known. And this one is the case on the online social network. In the online social network, we can see that, for example, if we have some user already infected by hoax, for example, here, and the blue one is the one that already realized that the hoax is actually the hoax, right? So this is the epidemic model, the structure of epidemic model that take place in this presentation. And I will give some introduction that in the epidemic model we have two kind of things, how the nodes or the user will have the states during the infection. The infection here means you can get the hoax, or you can get the how to say, the disease. But in this presentation, I will be focusing on the infected, mean infected from the hoax or catching the hoax, right? The first model, we call it the SIS model. In SIS model, we have the susceptible, infected, and susceptible. Susceptible means the healthy user. The healthy user means that the user that have no hoax. And the infected user means the user that have catching the hoax. Right? Each user will have a certain probability that called the infection rate to become infected. And also, its infected user will have a certain probability that will be recovered or will be realized that the hoax is not true. So we call it the recovery rate. We represent it as a delta here. So in SIS model, we have only susceptible to become infected, and then with a certain probability, it will come susceptible again. And the second model is called the SIR model. In SIR model, this is the same with the SIS model, but every infected user, after recover, it will become resistant or immune from any infection. So it will not be infected again. In the first one, after getting recovered, being susceptible, it can become infected again. But in the SIR model, after it's recovered, it will resistant to any infection in the future, to any hoax in the future. So in the network, we can easily see that if the user here catching the hoax, meaning the red color mean catching the hoax, it will have the probability to infect others, not easily, but will have a probability to infect other with beta rate. And also we have the recovery rate delta to become healthy again. And in SIR model as well as like that. So I will introduce our first proposal that we call it the preemptive graph protection strategy. The graph protection strategy is the strategy to solve the graph protection problem that I previously mentioned. This one is implemented on the single layer static network. So we assume that the network is only a very simple, a single layer and static, will not change over time. So what does the preemptive mean? The preemptive strategies means that we have to protect the graph before the attacks. So before the attack, we should select which node that should be protected first. The state-of-the-art method in this preemptive strategies is called the net shield by Chen in 2016. Dr. Chen in 2016 mentioned that how we can select the nodes. She mentioned that we can use the connectivity criterion, that is the largest eigenvalue of the adjacency matrix. So, for example, we have the adjacency matrix of its graph here, and the lambda or the largest eigenvalue will indicate how connected of each graph itself. So, and we can see here that all of these three graph has the same number of nodes, 5. but they have a different lambda, different largest eigenvalue. The clique itself have lambda equal to 4, and star have lambda equal to 2, and chain lambda equal to 1.73. And we can see here that the more connected the graph is, the largest eigenvalue or the connectivity criterion of this graph itself. And just to make sure that the largest eigenvalue or the lambda is belong to the graph. So how to calculate which node that should be selected? So its node will be associated with the principal eigenvector of the lambda. So the number of principal eigenvector is same with the number of the nodes. Right? So this one is from Dr. Chen in 2016. And this one is from the Prakash in 2012. He mentioned that the lambda, or the largest eigenvalue, has the big role in the determining the epidemic threshold of epidemic model in the arbitrary networks. So he mentioned that if the propagation strength is less than 1 over the largest eigenvalue, or 1 over lambda, there will not be any epidemic. So there will not be any hoax spreading. So the largest eigenvalue or lambda will determine the whether the epidemic or the hoax spreading will be happen or not. So what she proposed. So Dr. Chen actually mentioned that the netsheet it selects the protected nodes from all possible combination of k nodes, which maximize the following formula. In this formula, we make the shield value of the set of nodes. How to calculate it? That is
Hello, Mr.
the highest.
Arie. Hello. I
Yes,
have a
hello.
question. Yeah, I have a simple question. How you know
Yeah.
that a graph is connected?
Sorry.
How to know that a graph is connected? Very simple,
Yeah.
basic question I'm asking.
Yes. If the graph, if the graph is connected, then the second smallest Laplacian eigenvalue will be equal to 0. Yeah.
Again.
The second smallest eigenvalue, Laplacian eigenvalue, will be equal to 0. So that will be the graph is connected.
Very good. Please proceed, please.
Okay. All right. So the first one, the first formula will select the nodes that has highest the connectivity, and also the second one will give penalty for the adjacent nodes. So this one has the weaknesses as well. The first one is time consuming because it calculates from all possible combination, right? And the second one, the weaknesses is ignore the importance of the degree centrality. So they only consider about the connectivity itself, but the degree centrality is not considered here, which protect the dense area of the network. So what we propose is the first one, we still use the connectivity criterion, the largest eigenvalue, and combine it with the degree centrality to find the node with the highest degree value that located in the dense area. Because of both of the criteria has different order of magnitude, and we assume that they have the same importance, and without requirement of the normalization. So based on the Gerasimov multi-criteria optimization, we can use the product formulation. Right? For example, here in the karate network, we can see that the degree centrality will have the highest value in the center of the graph, the dense part, and the principal eigenvector, which having the large the nodes that having the high value of principal eigenvector will have the high value as well in the nodes that connecting to cluster. So in here we want to get the nodes from the dense part and the two connecting part, the principal eigenvector. This one is quite easy, but this is practical, right? And if we can see that in the couple Erdős Rényi network, yeah. In principle eigenvector, if we have the Erdős Rényi network, which have the same number of nodes, we can easily find the nodes that connecting the two cluster having the high values, the principal eigenvector. So we should combine both of them, but this one is very practical, right? And what we found is from the net shell, we have an additional improvement of the number of ratio of surviving nodes. Not that much that we have an additional, because it left some of the highest degree as well. Right? So, but in terms of the running time, because we don't check all of the possible combination, but we make a ranking based on the largest principal eigenvector and the largest degree centrality, so we can make it really faster. So for example, a running time of a net shell in the DBLP citation with 12,000 nodes, in Netshed, you need more than 3,000 seconds. But in GraphSheet, you need just less than 1 second. And in the Cora citation, with 23,000 nodes, you can have just less than 2 seconds against the Netshed, which is around or almost 10,000 seconds. Right? So the GraphSheet runs much faster and protect a little bit more than the net shield, even it not that much, but it runs faster. Right? Okay, so if we can see the compared to the larger graph, so for example, a 16,000 nodes, this is the graph of Yahoo Advertiser. So we can see that the graph shield and the net shield is runs really faster. And the NetShell Plus is actually the improvement of the NetShell that proposed also by the Dr. Chen, that use the iterative addition to the selection. Yeah. But after that, we need to know the sensitivity of the parameter, whether our proposal, the graph shield, is sensitive to the epidemic parameters or not. So for example, if we change the infection rate, or if we change the recovery rate, or if we change the epidemic propagation rate. So we tried on the Barabasi-Albert network with 1,000 nodes and the average degree of 10. Then we average it after 100 simulation. So we can see that the graph shield is the green one here, Among the other competitor, it gives always the survival ratio, the highest survival ratio. And we can see that if the infection rate is very small, then the survival ratio of all of the methods will achieve the best. And how if we change the recovery rate, as well as it graphs will maintain the good performance regardless the value of the recovery rates and the epidemic model. This one is on SIS model, and this one or SIR model. And how about if we change the ratio, the infection rate over the recovery rate, the beta over the delta, and we can have that all methods will reach the high ratio when the infection rate is low and the recovery rate is high. Right? And the graph shield, our proposal, all maintain the quite good, and in most cases we can say like it can reach the best among the other ones. So and in the first part, this one is very easy, and it's quite practical, not so theoretical. So we improve the critical node selection by combining the connectivity and the degree centrality from the previous state of the art. And the most importantly, the graph shield is way faster than the state of the art network. method. But there is a limitation here. There is a potential issue of non-convergence because we use the eigen decomposition process and we use the power method approximation. So there is a potential issue of non-convergence. Right? And the second one, that the principal eigenvector is not theoretically designed to find the correct cluster. Right. So in the second part, we want to handle this kind of limitation. And also we want to have a challenge how to handle it in the multiple layer of the network. The multiple layer of network, usually we call it the multiplex networks. Multiplex network is a network with the multiple layer where the same set of nodes appear in the different layer. So for example, a same user or a same people have the account in Facebook as well as have the account in Twitter and Instagram, but they have a different friends. They have different friends on Facebook and they have different friends on Twitter as well as in Instagram. So we just call it the multiplex network. Right. It is harder because usually if you focus on the first one on the Facebook, maybe you will miss the structure on the Twitter and as well as in Instagram. So how to make it simultaneously? The state-of-the-art method in here is called the spreading degree by Chow in 2014. They use two kind of things. The first one is centrality criterion. They use the degree centrality and layer-wise infection rate. So it means that the infection rate in each layer will be considered. And it protects the node with the highest multiplication of the degree value and the infection rate. The strength one is it's already considered the dissimilarity of infection rating in each layer. But the weakness one is the protection are to focus on the dense part of the network. So this one is still quite easy and practical. So we want to handle the multiplex network as well as we want to improve our previous selection. If in the previous one, we only use the standard largest eigenvalue, which has some limitation. So in here, we use the random walk normalized fiddle factor. The fiddle factor is the second smallest eigenvalue of the Laplacian matrix. And the random walk normalized fiddle factor means that we have the eigenvector of the second smallest eigenvalue of random walk normalized Laplacian. It's already proven that this one is usually used by the spectral cut. I think most of you is already know this old method. We can find the normalized cut. The normalized cut is the spectral cluster, and so we can find the bridge, the nodes that become the bridge between the spectral cluster. So we want to improve that kind of thing. Instead of only using the uh, principal eigenvector, we want to make it robust by using the random walk normalized Peter factor. And also we still use the degree centrality as well as in the previous part. And not only we use the layer-wise infection rate, but also we will consider the layer-wise recovery rate. So in here, it's very easy. We can just use the protection value by calculating the spectral property, the random walk normalized feeder factor, and multiply it with the degree centrality. And then we'll multiply it with the layer-wise epidemic propagation rate. So it still maintains the practicality of all of the criterion. So this is the schematic illustration of how we can find the center and bridges in the graph. If you want to try, we have some, this is the toy graph, right? This is the input graph. We can see actually we have a tree cluster here. This one, the first one, second one, and the third one. Right? Using the random walk normalized feeder factor, we can find the nodes that become the bridge based on the random walk normalized feeder factor. And using the degree centrality, we can find the center of the nodes, I'm sorry, the center of the cluster. So by combining both of them, protecting the bridge and protecting the centers, we will protect the most important nodes here, not only the core cluster, but also the bridges as well. And yeah, again, our competitor, we can improve the protection of the existing state of the art. And this is the data set that usually used to evaluate the effectiveness of this graph. And we use the student t-test to check whether this result is significant or not. And if we show the scalability, or for sure, comparing to the graph shield, the previous graph shield, this one is a bit expensive. So the complexity is not linear, but it's almost linear. We can see here the peak of complexity, but we can see that the running time of the our proposal based on this complexity is almost linear with respect to the changing of the size of network, as well as the protection budget. The K is the protection budget, N is the number of nodes, and M is the number of layer. So again, we can see the parameter sensitivity. Yeah, I think this one is quite the same as the previous one. So we fix the recovery rate and the protection budget, and we change the infection rate. So the recovery rate is fixed at 0. 0.5, for example, and the recovery rate will be changed from 0. 0.1, 0. 0.2, and so on. And we want to know how about the survival ratio. And we see here that the multiplex shield, our proposal, is better than the graph shield, our previous one, the graph shield. Why? Because in the graph shield, the our previous proposal, it ignored the dissimilarity between layer, so it gives less effective protection than this one. And as well as we improve the selection using the random walk normalized feeder vector instead of only the principal eigenvector. This one is the similar one using if we fix the infection rate and the protection budget, and we want to know the sensitivity to the recovery rate. And this one, the latest one, we can see that the similar one, if we fix only the protection budget, what will happen? And we know that all methods will reach the highest ratio of surviving nodes when the infection rate is very low and the recovery rate is very high. So in the contribution of this, our second part, we improve our critical selection by introducing the random walk normalized feeder vector, which wants to find the spectral cut or the spectral cluster of the graph. So we introduced the spectral property criterion. So we found that this proposal improved the effectiveness, but we still have the limitation as well. The limitation is that there's a still potential issue of non-convergence still exists because we still use the eigen decomposition. But the critical nodes selection is still based on the individual node base. We know that if you combine the nodes A and B and C, which is the best performing, it will not always give you the best performance comparing to if you see it from the a set of nodes, right? So the best performed nodes, if combined to each other, will not always give the best result comparing if you check the all combination of the nodes, right? So in this one, we want to go to uh, the third part, which is we will use the reinforcement learning. Yeah. In this part, we also want to challenge ourselves with the dynamic network or dynamic graph. The dynamic network is the network which its structure changes over time. So for example, in this graph, we have a new node here. We have a new node here, and we also have the new node here. The node and edges changes over time. So what is the definition? In this, the definition, there are two definitions that is quite popular. The one is by Becker in 2018. It mentioned that the dynamic network can be divided into the snapshot, the first snapshot, second snapshot, and the third snapshot. The snapshot of the dynamic graph will consist of the nodes and edges that are active at that given time step, or by Chuang in 2013 at a given interval, not a given time step, but a given time interval. So this one is quite same, but we divide the dynamic network by the snapshot of the static one. So how to handle the previous limitation? This one, the previous, this is very important because our selection is still based on the individual node-based criteria. So we introduce the new criteria using the minimum vertex cover. Minimum vertex cover is actually quite popular, but I will introduce a bit here. Vertex cover is the set of nodes. Yeah. So let's say we have the input graph here. 7 nodes. We have the 7 nodes. Vertex cover is the set of nodes that will cover all of the edges. All right, all of the edges in the graph. All of the edges in the graph. And the minimum vertex cover is the vertex cover that has the smallest size, or the minimum size. So here we can see that from the 7 nodes here, the graph 7 nodes, only by protecting three, yeah, three, 1, 2, 3, we already protecting all of the connection, all of the edges in the graph. So it makes sure that with this 3 node, there will not be any hoax spread throughout the network. Yeah, but you can see here that not always the best or the highest score of the nodes will give the best one. So for example, this one, these nodes have the degree 3, 1, 2, and 3, but it's not selected compared to this one, this node. This node only have 2, but it's selected because we see it not as an individual, but as a set of nodes. Set of nodes. So we combine these 3, 1, 2, and 3 instead of 1, 2, and this one. Right? Even though that this one has the highest degree in here. So this one we change from the individual node selection to the set of node selection. We go to here. And we mentioned here that this one is called as the protection threshold. So this is the threshold that there is a threshold that you can just achieve by just protecting that number of user of nodes. You can just protect all of the network with the minimum size. Yeah. So how to represent that? How to represent which node that should be selected? The first one, we should store, right, the information about the neighbor structure, because you want to know that this nodes has neighbor this node and this node, and this node have the neighbor this one and this one. So you want to store the information of the neighbor. So how we store the information of the neighbor? We use the node embedding. In node embedding, we store the information about the neighbor structure by the encoding function. So we will store each node into a vector. And in each node will be the fixed size of vector. The vector here will be the feature vector that we can use for any machine learning or deep learning methods. And we can save the neighborhood structure here. But how, right? How? So aggregating information from the neighboring nodes is quite hard. So for example, we have the target nodes A here, and this is the input graph. So you want to aggregate the information from B, from D, and from C, right? So let's say the first one, you want to aggregate, yeah, you want to aggregate that node A should be from the node B, C, and D, right? So from B, C, and D, right?
Cái
But the B,
cái
the
này là
nodes, sorry,
phim thằng Long ấy đâu có để đâu đấy.
yeah, okay. So the nodes P has two neighbor, node A and node C, right? So we just combine the information from node A to C to B itself, and so on, right? And so on. And you can see that once you target the nodes A as a target node, it will appear here again because we want to aggregate the information. But how, right? How? So what is the content of this box, right? What is the content of this box? One of there are many methods to aggregate the information, but the one that we can parameterize is we can use the neural networks to aggregate the information, and this one is quite popular, how we can aggregate the information by parameterizing the parameter as well, the neural network. The first one by graph convolutional networks by Kip and Welling in iClear 2017. So they use the linear and ReLU function, and the aggregating function, they use the mean, the average of all of these nodes. The second one by graph sheets by Hamilton in NeurIPS in 2017. So instead of using the linear and ReLU function, they use the max pooling and use the MLP for the aggregating, this one. So how about how we can use this encoding function, the embedding function in the minimum vertex cover? Yeah. So what we propose here is we use for each node, the feature factor will be calculated by using the node on feature and the neighbor feature and the neighbor edge weight, and each of them we can use the ReLU function. So for example, these nodes, the node fee will be get the information from this node and this node. And so for example, this node fee is selected as the MVC, and this node is not selected as the MVC. The tag is 0 as well. So then the edge weight is 5 and 3. So we just can combine it together. And we repeat this process by t times to represent how many hops. So the first hop or the third hop, and so on, right? The first step of neighborhood or the second step of neighborhood, and how large the cluster that we will produce. So after that, we can estimate, the function that we can just call it the Q function, the quality function, the Q function of selecting the nodes phi, given the current state of the graph. So the current state of the graph is embedded as the HS, and based on the pooled embedding of the entire graph, this one, and the embedding of the nodes phi, and all of them, we can use it, parameterize it, and in the neural network. So every parameter here can be parameterized, and if you know for example, in this graph, so how you can find the its node, which should be the best for the minimum vertex cover. We can use the trial and error, right? We can use the trial and error, or we can use it smarter. We can use the reinforcement learning. So instead of trial and error, we accumulate uh, the the objective function, or the rewards. In reinforcement learning, we accumulate the rewards, so we can have the highest reward in the end. So here, the Q function, the quality function, we can use it as well in the deep Q network. This one is the deep learning on the reinforcement learning. So in the reinforcement learning setting, the minimum vertex cover, we can appoint the rewards equal to -1 as a penalty. Why? because you want to have at minimum, right? The more node you include to the MVC, the worse it is, right? You want to keep it the minimum size. You want to keep it the minimum size. So we give the, instead of we give the reward, we give the penalty, -1. And the state itself is the current selected nodes. The current selected nodes. So for example, in this graph, the node V is already selected as the MVC part solution. Which node that should be selected? Maybe this node or this node, right? So we evaluate it by this Q function. This Q function based on the embedding of the whole graph and the embedding of the node V. Okay? And we can just use it the action value function. So we can just select the largest score. The largest score is quite easy because we already have the Q function. We have already the Q function, and we can just get the nodes that having the largest Q function. Yeah, the largest Q function, and then we can just add the best nodes to the cover, or add the best vertex to the cover. Yeah, so at the end we can have the minimum vertex cover. So what we propose to handle the dynamic graph, we already proposed to use how to find the minimum vertex cover using reinforcement learning here. So in the dynamic graph, we have a given graph, the temporal snapshot, and we have the embedding of its nodes, right? And then we use the deep Q network to parameterize, right? And then we can have the Q value, or the result of Q function for its node, right? So by comparing the Q value, or the result of Q function of each node, we can have which one that have the best or the largest Q value, and that node should be selected. And that node should be selected as the MVC. And that node should be selected to be protected against the hoax. Yeah, that's our proposal. And this is our evaluation. This one on synthetic network generated by a tensor library on temporal snapshot. Our proposal, we call it the reprotect, reinforcement learning protection. Yeah, we can beat the other methods. We can beat the other methods. And if we see here, our proposal called reprotect. Reprotect P is also our proposal, but we introduce the perturbation. Yeah, we can see here that with the increasing protection budget, our proposal, our method, reprotect and reprotect P, the green one and the orange one, always outperforming the other competitor in the dynamic network here. And the previous one on the synthetic network, how about in the real world networks? This one is on the Math Overflow High School Hypertext 2019 and the email networks. We find that our proposal, the reprotect and reprotect P, even the reprotect is outperforming the existing baseline method. And this is our improved methods using the perturbation. So it's also outperforming the existing baseline methods. Yeah, this is the example in high school data set. Yeah. So again, we check the sensitivity, the result. Against the other methods. Yeah, the sensitivity, it's quite sensitive actually to the infection rate, and as well as to the recovery rate. It's quite sensitive. So the larger infection rate, we can get the highest survival ratio, and the larger recovery rate, we can have the larger survival ratio as well. In this one is the ratio of the epidemic propagation rate as well. Yeah. So in summary here, we introduce the first one. We introduced the protection threshold using the minimum vertex cover. And also we improve the critical node selection from individual node base to the collective node base criteria. And we use the CNN architecture on reinforcement learning using the deep Q network for more scalable implementation. If you still remember our previous work, it used the eigen decomposition, which is quite expensive for the large network, large graph. But using the CNN architecture, we can handle maybe up until a million number of nodes. So and also the proposed one, it improved the effectiveness, but there is a limitation as well. The training process is expensive, yeah. So it's not suitable for the static network because it's the training process is expensive. So we introduced the approx degree method. So instead of using the reinforcement learning, we can just use the how to say the MVC estimation, just the MVC estimation without reinforcement learning. The MVC estimation based on the degree. So this one is the heuristic. So this can be used as an alternative. But this may be not quite good for the very large social network. And also the second limitation is the because of the definition of the dynamic network by Bakker and Zhuang that we use in this in this work is still based on the interval based discrete time step. So in the future we should focus on the continuous time step because that is really hard, but should be handled as well in the future. Yeah. So in conclusion, what we propose? Yeah. So given the social network. So, for example, the Facebook, we have the current snapshot of the social network structure. We can combine, we can use, and we have the protection budget. We have, we will propose this combined strategy, yeah, from the previous methods. Which one that should be used? The first question is the data from the multiple social network available? I mean, we can use the information from another social network to handle the current social network? If yes, then we can use the multiplex cell, our second one. If not, then we should ask whether we should use the quick response or not. If we need the quick response, then we can use the graph shift, which is very easy and uh, very fast because it's quite simple using the largest eigenvalue, and that's it. So yeah, so we can just use the graph shield. But if not, if you want to train it for the long term, you want to handle the hoax for the future for the long term, yeah, so we can use the reinforcement learning base, yeah, reinforcement learning. The in reinforcement learning, we should train on the previous snapshot of the network. Yeah. So if we have the previous snapshot, then we can train it. Yeah. And so we can use the reinforcement learning base. But if not, we can just approximate using the heuristic base. The heuristic base by approximating the minimum vertex cover. So the output one is the protected nodes here, yeah, the protected nodes. So it means that the critical user will be protected. Some future work are still left here. The first one, because we assume that the protection are on the wholly observable dynamic network, we should left or handle the partially observable. So how about if we don't know the whole structure of the network? We only know the partial structure. So because the real world social network are not only dynamic but also massive in size. Yeah, and obtaining the whole structure at any time stamp is hard and expensive. So this one is left for our future work, and maybe we can also collaborate as well. And the second one is the unconstrained graph protection. Yeah, in the constrained one here, we have another a subproblem that we can call it the maximum number, or we want to have the maximum number of connected component, or we want to minimize the size of the disconnected component, or we want to have the maximum threshold of the connected component. So the solution for different variant will be different. So the even the single node is protected. So this one will be left to our future work that maybe we can also collaborate later. So this is the just our publication related to this work. The first one and second one on the Springer Applied Network Science, and the conference is on IEEE Web Intelligence and IEEE Asonam. Yeah, I think yeah, this is just the appendix, the statistical significance evaluation using the independent two sample student t-test. Yeah, and the in most cases our proposal is significantly better against the state of the art in the single layer static network, or in the multiplex network, or even in the dynamic network. Yeah, in most cases we significantly better than the state of the art. Okay, I think this is the end of my talk, and I will be happy to answer your question, and or maybe we can discuss a bit more about this matter. Okay, thank you very much.
Okay, so thank you so much for your presentations. I see that your presentation is very useful for us, especially for the modeling of some epidemic model like CS model. Can you hear me?
Yeah, Professor. Yeah.
Yeah, yeah. Okay, so now we change to the second sections of the Arie conference today. And now sessions we have some questions and answer from Arie. So you have any question for presentations? Question. Any question? Okay, so uh,
And
in
also, I think I will send the modified slides to you, Professor, and maybe you can distribute to the all of the member here, and
yeah,
maybe we can also discuss later.
yeah, sure. Okay, so I will send the slide to on the audience here, so we can discuss more about the questions.
Yeah.
But have some questions. So I think that the most important things in your presentation is that you're working in dynamic networks. So
Yes.
in my opinion, that dynamic networks is not only in a different structure, but also in different informations in the graph. So what it means that so every time we have different informations for the node and edge. So how can we measure in improve the connections in case of we have a different information in the graph? Okay.
Right. That's true.
So can you give you a turn to slide 63? 63.
Yeah. Wait a moment. We'll
Yeah.
change. Yeah. Can you see it?
Yeah. Sure.
Okay. Yeah. Yeah. Thank you, Professor, for the question. So actually, that is the very good question. So. Uh, in the dynamic network, and you are right that the nodes and the edges will be changes, so the structure is changes, but also the information of its nodes and edges all will maybe changing as well. So for example, like the nodes here is the social media user. The social media user will be different to each other. One person have the different background or demographic background or something like that, and there will be changes as well. Yeah, that's true, that's correct. And that is also the limitation of our current work right now. We just focus on the structure, so we haven't including any feature information. So for example, the demographic characteristic, for example, or the age, or the sex attributes, or the how they interact to each other, for example. So that are still left to the future, and I think maybe we can also like uh, make some new research on that. And in this work, we only use the structure. We only consider about the structure, that all the nodes will be considered same. This node are same, but yeah, sometimes this node is Donald Trump and this node is just me, which is different. I and Donald Trump. Quite Donald Trump is quite important. I'm not, right? Right. So in this work, we still assume that all of the nodes or all of the user are same, but in real life it's not correct. So in the future, we should handle that kind of things as well.
Yeah,
Yeah, I hope it's answered the question.
yeah, I see. Yeah, I know that the problem of the dynamic network is very hard. It's really, really hard. But the point that when currently is we also had some many other research group in our team. We're doing in transfer learning.
Yeah, I
So
see, I see.
yeah, so one of my concern is that so how could we do transfer learning from
Mhm.
a model? From a model, we mean that from a graph and network to the other. So how
Yeah,
can
yeah.
you, yeah, how can we do the transfer learning? As you know that, for example, we have some
Mhm.
epidemic model of COVID-19, but
Yes.
we also have other epidemic model of other things like that.
Yeah.
So yeah,
True.
so we have taken a lot of time to make a model in a graph network. So how can you do transfer learning to the
Yeah,
other?
yeah. True. 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 Yeah, that's very good question, Professor. So let me share another file that I will introduce to you. So wait a moment, please. So actually, we can use the transfer learning as well in the dynamic network, and it already has done, and I already try it as well, and it can works as well. So it's quite good to be used. Right. Okay. So yeah, this one. Let me share the screen. Can you see my slide?
Yeah, yeah,
Yeah. Okay. So here we use the transfer learning. So this one is the example of the use of the transfer learning. So it approximates the minimum vertex cover, but this one, if you try to get the sorry, yeah, this one, sorry. So this one is the number of nodes in the graph. So for the small graph, 15 to 20 number of nodes, and for 40 to 50 number of nodes. This one actually you can train on the smaller graph and then test it on the larger graph. So we use actually the transfer learning. So that's also we already have the experiment on that, just a bit experiment. So we how to say we train the reinforcement learning on the smaller graph and then apply it on the larger graph, because training on the larger graph is very expensive. It's time consuming, so we can train it on the smaller graph and then apply it on the larger graph, but we should make sure that the distribution of the nodes should be somewhat similar. So in here that already used is if we use a certain network. For example, this one is the Erdos Renyi network that can be generated. So we can make sure that the network has smaller and the larger one is similar. So that's actually very interesting, Professor. Yeah, the
yeah,
transfer learning. Yeah.
yeah. I know that's well. The question is very hard.
Mhm.
So we have also have the other question from Professor Ling Chung. So Professor Ling Chung, can you show us your picture, the picture, and
Oh,
raise a question?
okay.
Yeah, raise questions.
Okay.
Professor Ling Chung is from the Vietnam National University.
I
So
see. I
he
see. Yeah.
graduated from the USA from a long time ago, and now he dean of the some smart laboratory in Wahyu. Okay. So Professor Len Chung, can you give some question for the presenter, Dr. Arie, please?
Hello. Yeah. Can you hear me? Hello?
Yes, yes, Professor.
Yeah,
Yeah.
actually, I put some questions on the chat panel,
I see.
trying to understand the things. I'm not working in this area anyway, but it's um, so I'm trying to understand what you are saying. Actually, it's interesting. It's interesting. I did some work on graph signal processing, which actually um, exploit this dynamic graph dynamic networks. Anyway, some questions that I put up there in the chat. Like the three questions there. Can you see it?
Oh yeah. Okay. Yeah. So okay.
So
Thank
yeah,
you,
simple questions.
Professor Trin.
Yeah.
Yeah, Professor Lin. Yeah. The first one is about the protection budget, right? The protection budget. The protection budget is actually the number of user that we are able to protect, right? Because for example, in Facebook, I don't know in Vietnam, but in Indonesia we have more than 100 million user. We could not protect all of them, but we can just protect maybe 1,000 or 2,000 or something. Yeah. So the protection budget is the number of user that we can protect for a moment. Yeah, that's the protection budget. Okay. I have it's an answer your question.
Yes. Yes.
Yeah. Okay. So the second one, how to know the hoax nodes in the first place? Yeah, by anomaly detection. Yeah, that's true. So the in this one we only handle the hoax mitigation. So if the hoax
Yeah.
is already there, hoax is already
Mm.
there, but
Mm.
the detection of hoax is, I think there are already a number of research about how to detect the hoax. Yeah, we can use the anomaly detection, or we can use some text mining and natural language processing
Mm.
and some kind of things. But yeah, we can combine it with this research, our research. But in our research, we assume that the hoax is already detected. Yeah, the hoax is already detected.
Yep.
So we just try to mitigate. Okay, so the third one of your question is, what is the logic behind the success selection of the important need? Okay, yeah, this is interesting. That is a way to interpret the solution physically rather than mathematically via solution. Yeah. Oh, yeah. Okay. So this
Yeah,
is
because
quite good. Yeah, quite good. Okay, quite good, Professor. So in this one, we use the survival ratio. Survival ratio. So for example, this one, survival ratio is the number of nodes or the number of user that's still active, that not infected. So for example, this one is the initial condition. During the hoax spreading, the survival ratio here is 0 because there is no nodes that's still healthy, for example. But in here, the number of nodes that's still healthy is 1, 2, 3, 4, 5. 5 out of 8. So the ratio is 5 out of 8. Yeah. So this one we can count it physically. Yeah. So this one that we use to to measure whether our method is successful or not. Yeah. I hope this one is answering your question, Professor. Yeah, I'm really happy to have your question.
Professor Ling, do you have any questions, comments? I think it is very useful and interesting.
Right.
Yeah, I hope I can I already answer your question, but yeah, we can discuss later as well, I think.
Yeah, I think I'll discuss with you later. Okay.
Okay, Professor Lin, thank you very much.
Yeah. Thank you very much.
Okay, so in our audience today, we have many professors from many countries. So may I introduce Professor Huang? Professor Huang is a vice is previously the rector president of Tham Kang University in Taiwan. Now
Oh,
he
I see.
just moved to Vietnam in last 2 years to working for embassies in Taiwan in Vietnam for science and technology. So may I invite Professor Huang for raising some question? Professor Huang, are you there?
Hello. Thank you very much, Professor Sun. Can you hear me? Hello?
Yeah, we can hear you, Professor Huang.
Okay. Thank you. Yeah, I'm glad to join today's seminar. Yeah. Thank you very much, Dr. Arie, for your presentation. It's excellent. And yeah, I think I'm not familiar with the topic, but I'm glad that I learned something tonight. Yeah, thank you very much.
Yeah, thank you very much, Professor Huang.
Yeah, thank you very much for Professor Huang, because as you know that he's very busy, so a lot of works, yeah, administration and so on. But sorry, he just spent some time for joining with us. Yeah, so thank you so much, Professor Huang.
Thank you, Professor Sun. Yeah.
Okay, so may I invite Professor Joe Janis from the University of Greece. Professor.
Hello, can you hear me?
Yeah, can you show the picture, the photos? Yeah, it's a bit long time and I cannot see you. Please show the picture. Yeah.
Hello.
Hello.
Can you hear me now? Can you see me?
You can hear you very well. Okay.
Thank you. Hello, everybody. Thank you very much, Professor Sean, for the invitation. I'm very glad. I'm very happy to be here with you. And I would like to congratulate Arie for the great work and the very interesting presentation. Just one question. Can I ask you a question? Does your approach apply also to temporal networks in general? That is, in case of networks whose links are active only at certain points in time.
Yeah, thank you, Professor.
Understand?
Yeah, thank you, Professor. Yeah, that's
Thank you.
interesting. Yeah, thank you. That's interesting, the temporal network. So actually in the terminology that we use, temporal network, we use the terminology dynamic network. The dynamic network is the network that the structure changes over time. So we just use another terminology, but it is indeed the temporal network. So our work is also handled the temporal network as well. Yeah. Thank you very much, Professor.
Thank you too.
Yeah. So may I introduce again, Professor George Janis is a very active researcher from Greece. He's also author of many journals and special issue in the British Journal in Elsevier and Speaker. So whenever you have any problems or any connections in terms of shortcomings and so on, you can connect him. Okay.
Yeah, for sure, Professor George. I'm sorry, I maybe I pronounce it incorrectly, but Professor Georgilis, maybe we can
Vasilis.
also Vasilis. Okay, sorry, I'm sorry, Professor Vasilis. Maybe we can also invite you later in Indonesia. Maybe during the COVID-19, we can invite you by online meeting like this, so you can share with us your knowledge as well to our student. Maybe if you want to share your knowledge to our student, we will be very happy.
Yeah, it will be a great pleasure for me. Thank you very much.
Yeah, thank you, Professor Vasilis.
Thank you
Okay.
too.
Thank you. So may I introduce again the Dr. Andrew Copper. Andrew Copper, are you there? Andrew Copper? Andrew Copper. Maybe he's out for a while.
Yeah, I think so.
The benefits of the online meeting. we cannot know each other. We doing, I don't know. Okay, so Omar, are you there? Omar.
I'm here. I'm here. I'm here.
Yeah. So please turn on picture, photo.
Okay.
So may I introduce Omar? He's from Nigeria. So please, Omar, can you have a question?
Yes, I actually came in a little late when the doctor was making his presentation.
Greeting, Dr. Omar.
Yeah,
Nice
yeah,
to meet
yeah.
you. Yeah, nice
Yeah,
to meet
nice
you.
to meet you. Yes. So when you were making your presentation, I actually came in a little late, but there was a particular slide when you were talking about clustering.
Right.
Yeah.
That's fine. I think we can send you the slides and we can discuss later, or maybe we can collaborate. I think as well.
Okay. Because I was interested in trying to know how you specify the data, because I saw that there are different types of data that you have put together in the same, and then to arrive at different clusters, and those data are of different genre. They are not of the same category.
Sure. That's true. Yeah.
Yes.
Okay. Thank you, Omar. So we're also waiting for the questions from the audience, and because we have a very useful presentations from Arie, and so let me introduce you again. Arie is working in ITB in Indonesia for a long time, and before he came to Japan in 2016 for studying the PhD degree in the Tokyo Institute of Technology. So I just met him and discussed with his supervisor, Dr. Ayu.
Yes, right.
Ayu for a long time. And now I just very happy. I'm just happy because now he very active researchers graduated his PhD degree, and also now he came back to Indonesia working in the university from the government. Is it right?
Yeah, that's true. I'm working
Yes.
in the government state university.
Yeah. So we just hope that we can meet personally in Vietnam or in Indonesia. I'm thinking maybe the next year in the 2022 or 2023. Okay.
Yeah. Let's sure. I hope we can meet in person after the
Yeah.
COVID-19 year.
Yeah, as you know that as our lab here in Vietnam, we have a very large member. I think that for not only in Hanoi, but also in other cities in Vietnam. So we also have the very close connections in different range of research area, from subcomputing, deep learning, and so on. So I think that one of the most benefits and advantage for our research is not only by working in your field, but also you can change to the other field. So we can make useful applications not only in research publications, but also in some software, some products in commercial. Okay.
That's true, Professor.
Yeah. So we also have the very good professors from Vietnam. Professor Tao, are you there? Professor Tao, can you have a question? Professor Tao. Professor Tao, are you there? Hello.
Maybe he's muted. That's Professor Cook Tawa Ungo, right?
I
I
think so.
think he's on video and he looks active, but maybe he's muted.
Yeah.
Yeah, I think so.
Yeah. So anybody, you have any question? Do you have any question? Maybe this field is very is really hard to understand.
Complicated.
It's really hard to understand.
Hello.
Okay.
Hello.
Hello, we can hear you.
Yeah.
Can you hear?
Yes, yes, we can hear you.
Okay, I am Long. I am Long. I am a PhD student now, and I'm very interested in your presentation today. Yes. So I would like to ask you one question.
Yes, please. Yes.
Yes, on the graph, it's a very really hard. So how to identify the nodes degree centrality on the graph? You mentioned on the graph seal or multiplex. So if a node get the highest degree centrality value, whether it's the same the most important node.
Yeah, that's true. Yeah.
Okay.
Okay. Thank you for the question. So actually, the question was how we can identify or we can measure the degree centrality of each nodes, right?
Exactly. Yes.
Yeah, if I'm not wrong. Okay. So how we can calculate the degree centrality is very easy. The degree means the number of neighbor, the number of nodes that connecting to that nodes. So let's say I have 3 friends. So it means that I have the degree 3. So that's the degree. The degree is the number of neighbors, the number of nodes that is connected. So the degree centrality means that the degree value, but it's normalized to the other nodes. So for example, the other nodes, we use the rescaling, the statistical method, the rescaling. So the normalization, the highest degree in the nodes. So for example, is 200, and the smallest degree is 1, right? So we can just normalize it into 0 to 1. Yeah, 200 is maybe 200 to the maximum. If you use the min-max scaling, so 200 over 200 is equal to 1. So for example, 1 over the minimum is 1 is 1 over the maximum 200 is 0.0 something. So the degree is the number of neighbors, but the degree centrality is just the degree value, but you normalize it, yeah, against the maximum degree in the graph. Am I answering your question, Mr. Long?
So can you show the methods or formula to get the degree centrality?
Yeah. Okay. Sure. Okay. I will share the screen.
Dr. Long, can you show the picture view?
Yeah. Sorry. Yeah.
Okay. Okay. So here, for example, I want to have the degree of these nodes, right?
Yeah.
The degree of this node. The degree of nodes here, it has 3 connection. 1, 2, 3, right? 3 connection. So this node has degree of 3. Right? So this node have the degree of 1. This node have the degree of 1 as well.
Yeah.
And so on. So we can calculate the degree of all the nodes. Right? So that is the degree value of each node. But the degree centrality value of each node is just the degree value, but it's normalized. So for example, in this graph, the highest degree is 3, right? 1, 2, 3. Yeah, this is the highest one. So every degree value will be divided to 3. So we can have the degree centrality from 0 to 1. So for example, this node has the degree value 1, but will have the degree centrality 1 over 3. Yeah, it's the same for all of other nodes. I hope you understand my my explanation.
Yes. See, I see.
Uh,
So I have one question.
Yeah, please.
Just so the social network is a very very hard to store, and so is on the traditional tool or application. So what application do you use to store so is after drawing the data from the social network?
Sorry again. Can you repeat your question?
Can you hear?
Yes, I can hear you.
Yes, I mean, the data you draw from the social network.
Right.
So it you can get a very big
Right.
data set. Yes. So what application do you use to show it or restore?
Ah.
Yeah.
Okay. So we can have many actually. We can have many. The data crawler. Data crawler. We have. You can find easily the library for data crawler, but not all of them is permitted by the social networks, right? So for example, for Facebook, we should use their API to crawl the data. So we should use their own API. For the Twitter as well, we should use their own API. For Instagram as well, we should use their own API. So it's not about the tool, but we should use their own API. Yeah, that's how we can use the data.
Mhm.
Hmm. Is that your question? The tools, right? Or
Yeah, I think so.
okay, right, right.
Yeah. Thank you.
Okay, thank you, Mr. Long.
yeah. So let me comment again. Mr. Long is currently now is working in the Ministry of Science and Technology of Vietnam. So he just working in the field of a knowledge graph.
Oh,
Okay.
I see. All right.
Yeah, noise graphs. So wikis emphasize that every node can be invented by so many different informations, like can have multiple medias, have pictures, have text, and so on. Okay, but what according to his question, I have raised another question. For example, as you know that the your path flight or path before relies on reinforcement learning. Okay,
Yeah.
but as you know that the major problem of reinforcement learning, and you can see in the many textbook of the data mining or machine learning and so on, that is that it can lead to a lot of steps and also is need a lot of data and computations. So what do you think that we can change? We can that for some other graph, local graph, we can use different learning. So for is it, what do you mean that it not apply reinforcement learning for all graph, but it's just for a small local graph.
Yeah. So I think if I'm not wrong, if I got your question correctly, so the question is about the computational expensiveness of the reinforcement learning, because
Yeah,
training
yeah,
the reinforcement learning is very expensive, right? So and it can lead to very huge computation. So in this work, that's why maybe we don't use the traditional reinforcement learning, but we use the deep learning base. In the deep learning base, we use the convolutional neural networks, and you already know that the convolutional neural network is very scalable. We can handle quite a big data because we have a batch processing. So not all of the networks is handled at once, but we can handle with batches. So for example, 100 nodes first, and then another 100 nodes, and then another 100, and then another 100, and so on. So because of this batch processing, so we can handle a quite large social network. I hope I can answer your question if I'm not wrong and if I got your question correctly.
Yeah, that's correct. But what I see in your first slide that you use some very special techniques for sampling. For example, if for part 5, you capture informations from the graph structure, but how could we capture information, richer informations from the graph to sampling? As you know that we have a dynamic network, which means that we have a temporal network every time. So from from my from uh, from my experience, we can use some kind of a temporal work sampling from that stream. I remember that it's published in the last year. It's called the stream walk. You didn't know that? Stream walk.
Yeah, sure. Yeah.
Stream walk. Do you apply stream walk in yeah, your model?
Okay. Okay, that's very good question actually. So I will explain it a bit. So actually, the sample that we use here is we sample on the time step. So you mentioned about the stream that the network always changing, right? The network always changing. So in the stream one, actually it's a continuous time, right? It's continuous time. But here, what we use is we sample on the time step. So for example, we have the condition of the network at current time, and then we process it, and then we have another capture of another time, and then we process it again. So the sample here is the samples on the time, not on the graph itself, because the time here we assume that it is still discrete. Yeah, so yeah, you are correct that in the continuous one, in the stream one, it should be continuous, right? So from one, not directly to two, but 1.1, 1.2, and so on, right? 1 point and so on. It should be stream. It should be continuous. And I mentioned that that is the limitation. So we sampled on the discrete one. Yeah, it's very good if we try to combine this one with the stream processing. Yeah, so we can use the continuous version.
Yeah.
Yeah, I hope I answer your question, Professor Son. So yeah, it's actually very interesting.
Yeah, I understand. So may I introduce again? We also have a very prestigious professor from Vietnam, Professor Tao, Ngô Quốc Tạo. He's also on a dry skin. Okay, so we are happy to have him today for attending the conference seminars. And so, please, could you have any questions or do you have any comments for his presentation, please, Professor Tao?
Sorry, I very late today. I'm sorry. But, I have a lot with the moon. No, sorry, the professor sorry. I have no attend from 8 o'clock. I'm at the doctor, but I don't understand.
I see, I see. Okay, thank you, Professor.
The professor, he is just coming to seminars and yeah. So we will also have the audience here. Most of the audience here is a graduate or PhD in Vietnam or in other country in the world. So may I introduce Dr. Singh? Dr. Singh, he just graduates like Arie. He just graduates PhD, and he also have internship time in the UK's, working with many professionals in the UK's. So, Dr. Singh, could you have any questions? Dr. Singh, are you there? Dr. Singh? Dr. Singh, are you there? Oh. Yeah. Maybe he just outside for time. So you have any comments or question here for all the audience? Any comment and question? Yeah, no. Yeah. Okay. So I think okay. I think is no question. So I think it's time for the ending of the seminar today. If anybody here already have questions, please send him message or send me your questions and comment and send him directly. So once again, we just thank Dr. Arie for his presentations, and we hope that we can have other good and fruitful presentations of Dr. Arie in next time. But yeah, we also have many good further discussions raised from the comments of the on the in here. So we hope that we can make more research in the future. Especially, I emphasize on transfer learning and a knowledge graph. Knowledge graph, we have Mr. Long, Mr. Long here, over there. He's just working in knowledge graphs. And also we have other research field. So I think that we will invite Dr. Arie for working with us in the next time. Okay. So thank you so much. Thank you so much for the presentation. Thank you, Dr. Arie, and thank you all the audience for joining with us in the seminar today. And I just emphasize that we will have the other speaker for the next 2 week. Next 2 week, I will inform you for the schedule very soon. And I just have some time for confirming with the other speaker. Okay. So
Thank you, Professor Sor.
Thank you so much again, and wish you good health and success. And don't forget to join with us. Thank you. Thank you.
Thank you. Thank you, Professor Sons. Thank you, Professor Vasilis. Thank you, Professor Omar, and the other professor, and all of the participants. I put my email address in the chat box, so maybe we can also discuss later. Thank you very much. Yeah. Good evening.
Thank you, Arie. Good night.
Thank you, Professor.
Thank you, Arie, for your presentation, and see you next
Bye.
time.
Thank you very much.
See you.
Rồi, chán lại cứng.
Well, good night, everyone, and see you next time.
See you tomorrow. Juan?
Yeah, see you tomorrow, Professor Juan.
Yes.
Goodbye.